Okay. So today our goal is to learn about arc length, and that's our one and only goal. So our goal is to learn to calculate arc length for parametric curves. So to motivate that a little bit, I'm going to take and I'm going to draw a little squiggle line. So here is a little squiggle line, and we are going from, say, this point here, point A, to this point over here, point B. So what I want you to think is I want you to think about this question. How long does it take to get to Modesto? So when you're thinking about how do I get from here or from somewhere to somewhere else, there's some path you're going to take, right? And depending on the path you take, that might change the time it takes, right? That's essentially different arcs have different lengths. In this case, I'm not actually going to talk about time. I'm going to talk about distance, right? So my driving question here is how far is it to Modesto? And we're not going to answer this by answering a time, right? We're not going to say it's 45 minutes to Modesto. We're going to actually figure out in miles how far it is. So the way we're going to do that is we're going to think, well, look, if I drive from here to there, I could do something like think, okay, I looked at my speedometer once on the way, and it said I was going 60 miles an hour, and it took me an hour to drive there. So I do this thing where I go, distance is rate times time, right? You guys remember this? And I might say, okay, so the distance that I went is the 60 miles per hour I was going at the one time I checked, times the 1 hour that it took me. So I cancel some hours, I get that it's 60 miles. That's a pretty coarse approximation because I only looked at the speedometer once. That's not really how we do, right? So what we might do instead is say, okay, so instead of looking at it once, let's actually do this thing where we say, all right, distance is approximately the sum of rates times times. So we're going to split our journey up into little pieces, right? So we're going to say, we're going to go for a while and say every 10 minutes, I'm going to look at the speedometer and I'm going to say, all right, for the next 10 minutes, I'm going to assume that I'm going whatever speed I'm going now. Is that a great choice? No, but it does account for some stuff. So here's the stuff it accounts for. Say out of Sonora, I'm going kind of slow, right? Here's my velocity vector. It's kind of short because it's kind of small. That's what happens when I'm close to Sonora. After I get past Jamestown, I go a little faster. Right? So I have a faster, bigger tangent vector, right? Then down in here, we're cruising down towards Knights Ferry. That shit's really fast, right? So I have big tangent vectors down in there. You see these big old tangent vectors. That's me going nice and fast. Oops, that was kind of a crappy arrow. Big old tangent vectors going nice and fast. Then I get to someplace like Oakdale and I slow way down, right? Then I come through it a little bit, get going a little faster. Then traffic slows down again. Traffic slows down again. Then I get a little burst of speed. Then traffic slows down again, and then I get to Modesto, right? So I've got all my little tangent lines. Those are really my kind of at separate time intervals, right? I have different velocity vectors, and they're smaller or bigger. The trouble here, right? Like calculus wise, is that these are velocity vectors. What I really want them to be is I want them to be something about the speedometer when I look at the car. So I need you guys to think, what's the relationship between velocity and speed? So speed is the rate at which I'm picking up distance, right? That's this R. This R up here is going to be speed. So I'm going to speed times time. And so if I'm calculating distance, I need to know the speed. What I've got is actually a velocity function, right? So the calculus wise thing I've got is I've got a function that's like p as a vector function of t, or I've got v as a vector function of t, or I could even go one further and get acceleration as a vector function of t, right? But what I really, really want is I really, really want to take and figure out what the arc length of the position function is, right? So here's my position function drawn out, and I've left off all the kind of vector tails, right? So someplace over here is the origin, and we've got vectors that point up at this curve. I've left all those off because they're hard to understand and kind of crappy to draw. So we're just going to say, screw it. Here's my position curve, right? Each of these little vectors represents a velocity at a different time. Now, I still need that relationship between velocity and speed. Velocity is a direction and a magnitude, right? It's a vector. It tells us how fast we're going and in what direction. So the direction part's probably the direction part. What does that make the how fast part? Awesome. Makes it the absolute value, right? The magnitude of the velocity vector is the speed. So magnitude of velocity is speed. So what I want to do is I want to take and I want to add up over the curve, right? So I'm going to add up from a starting time A, so that's a time A, to a time B. And I don't want to add up the positions because I don't care where I am. I want to add up the absolute value, right? In this case, the magnitude of V of t. So I'm going to add up the absolute value, the magnitude of P prime of t dt. And this is going to be the arc length. So this is equal to arc length along P from A to B. And that does assume that this B here is what you get when you plug in the little value B for T. And this value A here, right, this point A, is what you get when you plug in the value little a into your position function. So I'm saying at time A, little a, I'm at point capital A, which is the end of vector P of A. And then down here, at time B, little b, I'm at point capital B, which is the end of the vector P of B. Hope that makes sense. So that's my kind of setup here, right? So my next thing here is, all right, if it's really that easy, like these should be super doable. Here's the problem. If I put this right, like if I'm going to write this out coordinate wise, so this is also equal to the integral from A to B. Okay, what's the magnitude of, my position function's a vector, right? It's got like an X component, a Y component, a Z component. And I need to differentiate those, that's fine. But I'm gonna have to square them and add them up, right? So I'm gonna have X prime of T squared plus Y prime of T squared plus Z prime of T squared. And then all this junk needs to be underneath a square root. And then I need a dt at the end. So this gets kind of gross looking. And these integrals don't tend to be very easy. I'm hoping you're looking at this and be like, man, those are going to be some kind of crummy integrals. They're going to be hella tough. So I've got a little visual I want to spend some time building. But let me get some preliminaries out of the way for it. So the visual I want to spend my time building is I'm going to draw an ellipse like this. And I'm going to say, all right, this ellipse, so I think there's more or less the center. I'm going to say that this distance here is some value A. This distance here, oops, that's supposed to be vertical, Joe. This distance here is going to be some value B. I'm going to talk about this as being my position curve. I'm really interested in how far is it along the outside of this ellipse. In other words, the question I'm trying to answer, kind of example here, is what is the circumference of an ellipse? And the answer to this question is surprisingly really, really hard. So let's see what we can do to write down some stuff. So the first thing I'm going to need is a position function, right? So my position function is going to be, I need a way to go around this thing. Well, if it was a circle, I'd do something like cosine t and sine t, right? Okay, so right now, if I plug t equals 0 into these, the sine part zeroes out, the cosine part turns into 1, and okay, this point over here, so if I say, all right, let's assume the origin's in the middle, this should be the point a comma 0. Okay, so I need an a here. That'll make it so I start in the right place. Then the t's, because I use cosine and sine, should drive it counterclockwise around, because that's how angles drive the unit circle, right? And I just need to know about 90, right? So when I plug in time, say pi over 2, right? The cosine zeroes out, so this first component 0, and the sine part becomes 1. So there I'm going to need a b on that guy. So this is my curve. 0 is less than t is less than 2 pi. So that goes around exactly 1 time and doesn't overlap at the end. You can put it equals 2 here if you want. It doesn't really matter. It's just a point. So that's my position curve. Now I need a velocity curve, right? So I need p prime of t. So p prime of t is going to be, we need to differentiate a cosine t. Hoping that's not too rusty in your head. It's going to be minus a sine t. And we're going to differentiate b sine t. So we're going to get b cosine t. And our arc length, right? C is going to be the integral from 0 to 2 pi, the square root of negative a sine t squared plus b cosine t squared dt. I'm like, oh, hey, there's a sine squared plus a cosine squared in there. Maybe this is going to be easy. And the answer is no. Sadly, it's not. So in here, I've got a squared sine squared t and b squared cosine squared t. That's all under my square root, and I'm integrating that dt from 0 to 2 pi. And you can't do any better than this. This is just what it is. Unfortunately, this is a thing you have to do with a numerical method, and that's tough. So I'm going to show you a little thing I built. So here is an arc length calculator that I built in Desmos for ellipses. So you can see I've got adjustments for A and B. And so these are my adjusting the major and minor axis. Okay. And then, and I happen to know what the answer is for 1.8 because I used a different calculator. So those are my major and minor axis. You can see those adjust the size of the ellipse. Then I've got my position function built in here. I've got my velocity function built in here. Right? I just made a p of x and a v of x. I didn't use t's because there were a lot of t's. Now the blue curve, so I'm turning everything else off. Blue curve is just my path, right? It's a cosine t comma b sine t goes from 0 to 2 pi, boom, around. I've got this n equals 4. That's a divider, right? So I'm dividing this ellipse into 4 pieces. There's a little bit of calculation nonsense that goes on down here. I'll show you in a second. So what that does is I'm chunking the ellipse into 4 pieces. And so here are, let's make it something else so we can see it quick. So now we're chunking it into 7 pieces. And these are TP of L. So L is this list. That's all the values of 0 up to 2 pi. And each one of them includes, oh, and I wanted to go to 2 pi minus 2 pi over n here. And this, I just realized I made a little mistake in it. Ha. Okay, so I've got 0 up to 2 pi less 1, right? So I'm not accidentally counting 0 twice. That's what my mistake was. So I've got 0 up to 2 pi minus 2 pi over n. So I've split this angle into 7 pieces. So I've got my L as my list of the 7 places we cut this circle. and then we'll ignore the other stuff for just a second. So I've got greens are going out from the origin. So when t is 0, they're 0. And then when t is 1, they're p of L. So p is the position function, and L is the various angles. So p of L's first element is this green arrow here. P of L is actually this point at the end, and t times it gives us this vector kind of looking thing. So the greens are basically the position vectors for all the special spots. And the purples are the velocity vectors. So that's TV of L. And the P of L just puts them tailed out at the right spots. So you can see I've got kind of a short velocity vector here, and then it gets a bit longer, and then it gets a bit longer, and then it's kind of shorter, and it's a little longer again, and then it's really long, and then it's kind of long-ish again. So you can see they kind of change over time. So if we bring this back down to something like n equals 4, you can see that the ones on the sides are considerably smaller than the ones on the top and bottom, right? So those are our velocity vectors, and the lengths of them are the speed. So down here in our calculation, I'm saying S. Let's see. S is S is a distance. Let's grab it with me. Let's call it D. Let's call it capital D because it's a list of distances. So each element of this list D is a little time, right? That's our 2 pi over n. That's how long did we make each measurement last. And then the speed that we were going at the beginning. So that's the absolute value, right? The magnitude of the velocity vector. And then down here at the bottom, I'm adding them all up. So if I crank on the number, so there's 127 chunks. And if we look down here, we've got 8.018. And if we keep cranking on this, right, so there's 700 now, 771 pieces. So I split 0 to 2 pi into 771 pieces. And in each one of those little times, right, this is just like I'm kind of constantly glancing down at the speedometer. And here I got 8.0189. Cool. So we can kind of tell that as we crank this thing up, oops, let's crank it all the way to 1,000. These first few numbers aren't changing anymore. I think that means we're pretty sure of them. Let's crank this puppy up a little bit. Oops. Uh-oh, I broke Desmos. Okay, so apparently you can't cut it into 100,000 pieces. Let's go back to 1,000. Okay, 1,000 seems to work. Let's try 10,000. 10,000 seem to work. I'm just waiting for it to update. Oh, 10,000 works. Oh, but I lost this. Oh, there's my calculation at the end. Okay, cool. I think that's pretty darn close to the arc length of that ellipse. I had a calculator up a second ago. Let me see if I can pull it out of my history. There's a really nasty technique called elliptical integration that you can use for these. I don't tend to show it to you guys because it's gross. So here's our circumference calculator, and we had 1.8 in for A and 0.6 in for B, and we're getting an approximation here. And our approximation here is 8.01894. And that is in fact just the answer I got rounded. Hell yeah. Super cool. I need to turn this down because Desmos doesn't like this. Okay, cool. So this is our kind of formula and thought for calculating arc length. The takeaway from this, the thing I want you to have most in your head, these integrals, if you make the slightest little error, this integral really gets screwy to solve. They're often kind of gross. If you make a little error, the book problems will have integrals that you don't know how to do. You got to be a little careful with this section. Don't forget to differentiate. Make sure that you're differentiating correctly. Make sure that you're integrating over the right bounds. The real thing is that this integrand is really hard to simplify sometimes. You might look for perfect squares in there. You guys know some other tricks. The Pythagorean trig identity is another trick you're going to have to use occasionally in here. Be aware those can be a little gross. You guys can do them, but this is going to be the worst section in the book for integrating. Can be tough. If all else fails, make yourself a little simulation or cram it in Wolfram Alpha. You guys can do this. It's just the simulation or the integration can be a little bit of a challenge. Thanks for watching, guys. Hope this helps. Oh, one more thing. Shit. Sorry. Let's go back and look at our picture. I forgot to say one thing. The one thing I forgot to say is that all of this does sort of assume that you're not retracing parts of the curve. So an easy assumption to add to this would be something like a little bit of a warning here. As long as P of T is 1 to 1. That's not actually a requirement. You could make a loop-de-loop in this and it would be fine. The requirement is really that it be 1 to 1 enough, like often enough. The real issue would be like if you took a section and literally backtracked it, that would be a problem. So I'm going to put an ish on here. You certainly can stop. So the velocity function can be 0. That's fine. You run into traffic lights all the time. It doesn't stop your odometer from working. If you want kind of a cool little thing, you could notice that your odometer is actually the arc length of all of the paths that your car has ever taken, as long as it wasn't towed, I guess. So that's kind of cool. All right, guys. Thank you for watching. Much appreciated. I will catch you on the next one.